Good morning, everyone. It's morning here in New York. I'm so pleased to have you join our training session, Guy Abel's training session. I'm Ellen Percy-Crayley, and I'm professor of geography and environmental studies at Colgate University in a very snowy upstate New York. My colleague, Professor Guy Abel, is at Shanghai University on the other side of the world. Isn't this just glorious? I see you from all over the world. Guy is a professor in the Asian Demographic Research Institute at Shanghai University, and he's my colleague on the IUSSP panel on international migration, strengthening the knowledge base for policy. And this training session is part of our effort on the panel to invest in you, to invest in the next generation, the current and the next generation of population scientists, to help us advance policy relevant and also scientifically relevant migration research and analysis. Guy Abel is a critical figure in this effort to, as he works with his colleague James Raymer, to develop a training manual on migration estimation, measurement, and analysis. And this training session is helping Guy and James advance that project, which we hope will come to fruition in the next few months. So I'm so honored to introduce and turn this session over to Guy Abel. Thank you.
Okay, thank you, Ellen. Yep, so I've sort of pre-recorded the training session and going through the slides, and I will put a link in the chat. You can download the slides and the material. I'll sort of explain it in the video, the structure of everything that we'll go through. And like Ellen said, this is sort of part of a handbook that we're developing with James Raymer. So any feedback on anything you can improve, or areas to cover, or just any detail would be much appreciated. And yeah, I think we'll stick around after the video finishes, so it runs about an hour and a half, maybe a bit under that, and then we can stick around for any questions, either during through the chat, or afterwards we can have a discussion. So maybe we leave it there, and then yeah, maybe Anna, you can play the video.
Okay, hello everyone. My name's Guy Abel. I'm a professor at Shanghai University and a researcher at IUSSP as well. So today I'm going to be talking about estimating, measuring, and working with migration data in R. And it's part of a handbook that we're developing for the IUSSP panel on international migration, led by Ellen. And in the manual, we're trying to develop sort of R code, R functions to sort of cover the techniques described in 2 UN DSA manuals and the migration chapters of the IUSSP online guide for the tools for demographic estimation. Let me just show you some links. So this is the links to the where the UN manuals are. So these manuals are fairly old now. I think they date back to the at least 20 years. And this is the tools for demographic estimation. And these again is a little bit old, 2012. But in both cases, both of these sources, none of them cover any sort of detail on how to run their methods, the techniques in R. So that is really what we are trying to do, as well as extend to some other areas in so to make it easier for our users to work with migration data and estimate migration data in R. So the outline of the handbook covers these 9 parts. So the first part, we talk a bit about migration data and concepts, and then the second part on handling migration data, and some summary migration indices, and the fourth part, estimating the migration, and the fifth part, describing and estimating age structures migration. So Rogers Castro migration schedules. Then part 6, we talk about describing bilateral migration data. Part 7, estimating bilateral migration. And part 8 and 9, so visual methods, so chord diagrams and Sankey plots, and how to do them in R. So today, because of time limitations, I'm just going to focus on part 2, part 7, and part 8 hopefully give you a flavor of what's coming in the handbook. So all the materials that I'm going through today are online in this Dropbox folder. So if you follow this short code, it will take you to the Dropbox folder that's here, where we've got all the materials there for you to download and have a play with in R. So that folder contains the PDFs that I'm showing you now, also the code that's used in the slides. You can run the scripts alongside, and some exercises and exercise solutions. I'll talk about a little bit about them in a second, and the data that we use in the slides and required for some of the exercises. So some general points before I get into it is that I'm assuming you have some knowledge of R, some familiarity with R, not a whole lot, but I'm going to use some sort of tidyverse functions, especially some dplyr, maybe a little bit of ggplot. Code will be there, and I'm not going to spend too much time explaining what's going on in those bits of code because it would take too much time. So I'm assuming you're sort of familiar with those parts of R. If you're not, there's a link to this bootcamp, our bootcamp page that has a nice tutorial on the tidyverse packages. And yeah, the sort of second point is that there are exercises for each part of the course. So for the 3 parts that I'm presenting, I put up the exercises. So previously I ran this course for all parts, and those exercises took the students around about 30 minutes, maybe up to an hour. For some users, it really depends on your background and your experience with R. I've also put the solutions to the exercises there. So usually, when I was running the course before, we would stop after each sort of set of slides and spend the next hour or so going through completing the exercises and then going through the solutions. Because of time constraints, I was in the class, but I guess if you're watching this back later after the conference, you might be able to pause the video and do that yourself. Yeah, and the final point is if you are having trouble installing R or RStudio or any of the packages that I'm using, I've set up this RStudio Cloud project where everything is already installed for you. So if you're really struggling with your computer, you can go follow the link to this R Cloud project. You can see you've got the folders there and all the R scripts to run, and I've installed all the packages, so it's sort of ready to go if you are struggling to get everything working on your computer. It's kind of a backup for you. And maybe the final point I should say is that during this showing of this video, I'm going to be on the chat on Zoom. So if you've got any questions, I can try and tick them in the chat section and provide answers there as we go along. Okay, so let's go on to the first set of slides proper, which is on handling migration data in R. So typically, when we think about migration data, we think about these sort of contingency tables, or what a statistician would call a set of contingency table. So these are sort of square tables that feel populated with values of migration. And in particular, the values on the non-diagonal parts representing some form of migration. So it might be a migration flow, might be a migration stock, and it's really telling you about the connections of how many people are moving or have moved between a set of regions. So the values in the diagonal cells represent some form of non-moving population. So it depends on the data source or the countries on what is typically used. So sometimes there are no diagonals, no values are provided. Sometimes the total populations might be provided, or there might be the number of moves within a region. It really varies from source to source. Okay, so some little bit of mathematical expressions that we are going to use later on to describe these contingency tables. So I'm going to use this notation M subscript I subscript J. So where I is representing the rows, the origins, and J is representing the columns, the destinations. And so I'm going to write any sort of migration flow matrix. This is MIJ. And sometimes you see written in the more technical sort of migration estimation papers, you might also see these notations with the pluses. So these pluses are sort of representing the sums of, in this case, the sums of the out-migration counts, the row totals. So we'll have, for example, we'll have 4 I's for 4 rows, and the 4 totals will be represented by this MI plus. And we also have the column totals will be denoted as M plus J. So summing over the rows to get each of the column totals. And then we could calculate a net migration for any region by subtracting the appropriate row totals from the appropriate column totals. And yeah, the last bit of notation is this M plus plus, which is the grand migration total, summing over all the sort of cell values in the contingency table. So yeah, like I said, we're going to use a bit of this notation later on, but it's not going to get too technical, I would say, for the most part. Okay, so some functions in R that are used to either describe or estimate migration require that as the input, you have a matrix type object rather than a data frame that you might be more familiar with. So matrices or matrix objects can be created using the matrix function. So the data is sort of the main argument required. And so this is where you feed in the data into the matrix object. And that is usually read into the matrix. So you sort of read in a particular order this data that you want to populate your matrix. So by default, what happens is that you give it a vector of values, and then it will sort of put them into columns. But we can change that behavior, sort of perhaps which might be more intuitive, is to read them in by rows by setting this by row argument is equal to true. So by default, that's false. So if we set that to false, then or didn't write this and had by default, then the data would have gone down like 0, 100, 30, 70, and so on, following the order in the vector. But here we set by rows equal to true, so it goes across. There are also arguments for the number of rows and the number of columns. So usually you can provide both, or you can just provide one, and it will work out from the length of the data vector how many columns there must be given the number of rows. And there are also options to provide naming names to the dimensions. So without providing the names, we would just see these sort of square bracket 1, square bracket 2, and square bracket 3, and so on. So we would just see the indices of the matrix. But it's often useful when working with migration data to provide these dimension names directly. You can really follow on which regions are sort of having these effects, and you can get more familiar with the data and pick out where there might be any data errors. So I'm just showing here an example, just creating the 4 region names, and then I'm providing those region names to the matrix function via this dim names argument, where it needs a list, an R list. So you need to give it, you can give the name of the first dimension, which in this case are our origins. So it provides this label here. And I set the origins to this vector R. And similar for the columns. I name the columns as destinations, and the R is the each individual column name that's provided. Okay, so in some cases we might be working with detailed migration data. By that I mean where we don't just have origin destination flows, but we have origin destination flows by one or more additional characteristics such as age or sex, or perhaps health status. So in this example, we can, for this kind of data, we can create arrays that sometimes when we come to estimation problems, we'll see later on, we need to provide arrays when we have detailed migration data. Again, in this case, just like matrix, it has a data argument where you provide a value. So here I just provided 32 random values between 1 and 100. And it reads them in again by columns, just as the matrix would have done by default. And then we have a dim argument that states that the dimensions of each of the dimensions of the data. So here we're saying we've got 4 rows, 4 columns, and then 2 tables. So each or the row number is always first, then the column number, and then sort of the dimension is third. And again, we can provide the dimension names using the dim names argument. And again, it has to be a list. So here we're saying the first dimension are origins, Second dimensions are destinations, and the third dimensions is a sex dimension defined as female and male. So then you can see it prints out the array here that's just based on some random data. Okay, so a useful function when you're sort of playing with matrices or arrays is the add margins function. So what the add margins function does is add some rows and columns to display the dimension sums. So for example, we run this add margins function on the matrix M0, and you see we have this from the 4x4 matrix. We now have an output with 5 rows and 5 columns with these additional sums. So it's a nice function in base R that we can use just to provide a quick overview and get an idea of the big sending and receiving countries or region, for example. Great. The add margins function has an argument margin, which allows you to subdue particular margins. So it tells you which dimension you want to sum over. So by default, that will be all the margins. But if you want just to, for instance, just sum over the rows, then we can set margin is equal to 1. Just get the column sums while we're summing over the rows. Yeah, data typically, when we get migration data in the wild, might not always come as a matrix. It certainly won't come as an array. And so we often have to do quite a bit of work to get the data into a matrix or array if that is what's required by, for example, some estimation functions. So there are a couple of useful functions in R that can convert data frames into matrices or arrays. And in particular, this xtab function is the fastest one, at least that I know of, and perhaps the most flexible. So this function converts data frames that we might typically get in the wild into a matrix or an array, and it has 2 arguments, a formula argument and a data argument. So the data arguments are quite straightforward. You're just telling it the data frame that you're going to want to convert. And the formula argument is telling you how you want to convert columns in that data frame. And so on the left-hand side of the formula will be the column in the data frame that you want to be used to populate the matrix or the array. So what's going to become the cell values. And then you use a tilde, just like you would do if you're familiar with sort of modeling in R, and you use a tilde to sort of show the equals sign in the equation. And then on the right-hand side, you have all the variables that cross-classify the dimensions, the data that you use on the left-hand side. So these are creating these dimension aspects of the data frame. And these are usually separated by a plus sign to say we're having multiple dimensions. So for example, this is just like a very basic data frame that we might have a migration, looking at the flows from A to A or A to B, for example. I just put the numbers 1 to 16. We want to convert that into a matrix. We can do that quickly using this xtabs function, where we pass the data frame D0 to the data, and we say the flow column is going to be what populates the cells of the matrix or the array, and the origin and destination columns are the categorical variables that are cross-classifying these the flow columns that we had before. So just go back. Remember, we had 3 columns: an origin, a destination, and a flow column. And we're using the flow column on the left-hand side of the equation. These are the values, and on the right-hand side we have the origin and destination categorical variables. Okay, so as opposed to xtabs, there's an as.dataframe.table function, which does the opposite of what we showed before. So it takes a matrix or an array and converts it to a data frame based on the array or the matrix dimensions. So the most useful argument to know about as.dataframe.table is the option called response name, and this allows you to set the column names based on the cells of the matrix or the array. So this is an example where we took that M2 data frame. Let's go back. This is the matrix that we have. We convert that back into a data frame by using M2. Then you use the pipe function here in R. So we take that M2 and then we convert it to as.dataframe.table. And as you see, it creates these data frame out of it. And by default, I think it will provide a column called a value here. But this is what response name is doing. It's setting the column name for the values for the elements of the matrix or array that were populating the matrix or array, and it wouldn't know what their name is. So this is where we set it to flow, for example. And the second part, or third line here, so even so just converting to a table because it has a slightly nicer printout function to display the data where I can see the data types that are being produced. Okay, and here's a second example with the M1 data. So that was the sex array. Let's go back and look at that. Yep. Nope. So we had the sex array. So if we had data like this and we wanted to convert it, perhaps it came out of an estimation function that we'll see later on, and we wanted to convert it to a data, then again, we can use as.dataframe.table. Yeah, this is the case where we took this sex array, we use as.dataframe.table. Again, we set the response name, this column name up here to flow, and convert to a table. So here we get 4 columns because we have the 3 dimensions of the array, and then the 4th column for the values that populated that array. Okay, so yeah, some other sort of tips for working with matrix objects. So sometimes when you've sort of created these matrix objects in R, it can be difficult to view them in the sort of R console. And that might be for many reasons, but 3 common ones are you might have very lengthy region names, you might have a very large unit size, so like your flows might be in hundreds of thousands or millions, or you might have large diagonal terms that are not of interest, but they might be, again, very big values that sort of spoil the printout of the data. So, and a good example of this is from one of these UN manuals, this object that I created, put into the MIGS package for lifetime migration flows between governments of the United Arab Republic, so what is Egypt today. You can see when we inspect this data, okay, thankfully we only have 11 or 12 regions here, but even then it sort of spans over multiple rows. So imagine you're working with a big matrix for like 50 origin or destinations. For example, if you're looking at the US internal migration data, then you would have a very big matrix, and it's often difficult to sort of follow, to sort of eyeball what's going on and get a good feeling of the data when you have such big dimensions. So one tip is to abbreviate the dimension names. And so we can do that by using the dim names function or the column names function and the row names function. So when we do dim names of the matrix object that we showed before for the United Arab Republic, we get the origin and destination sort of elements of the list. Yeah, returns a list with these two elements. And then we can abbreviate these names using the abbreviate function in base R. So abbreviate function sort of essentially it's like a little algorithm that's going to shorten the names, and you can specify like how short you want them using different arguments in abbreviate. And essentially, usually it just sort of picks out some vowels and makes the strings a little shorter. So here in this code, I've just made a copy of the object, and then I'm creating a new abbreviated region names. So again, it has to be a list, and then I'm going to take the row names and abbreviate them, and take the column names and abbreviate them and save them as the origin and destination components. So when I print out these new names using the abbreviate function, you can see Cairo, it drops the O, Alexandria, it will drop some of the vowels and sort of makes it short. So it tends to follow some sort of sensible patterns. And then I can apply those dimensions that are in R to the copy of the object here using the dim names object function on the left, which is a little unusual. And then we use the assign and then the values of the new dimension names. So you can see now we've printed it out, and now we only have like two columns that have spanned over, and it's sort of bunched up the data a bit more, making it a bit easier to view. Okay. So another sort of common problem that you might want to need help with is removing the diagonal terms. So sometimes, like in the in the stock data that I showed you before, we had values for in the diagonal terms that tended to be the biggest values in the matrix. And if you want to remove them, you can use the diag function. So just like we have with the dim names, use the diag function on the left. And here we're going to set the diagonal terms of this U1, this copy of U0 to 0. And when we print it out, we can see we get all the 0 values here. So again, a little unusual that we use a function on the left and a left on the left of the assign, but it works for these sort of base R functions of diag and dim. Okay, and a third operation that you might want to do is to scale the data to appropriate levels. So before, the data were in just person numbers, right? Not rounded. But if we wanted to round, for example, we can use the round function. And here I'm rounding the whole matrix, every element of the matrix, to the nearest 100, right? So I divide by 1,000, and I just give it to one decimal point. So we can see, for example, there's 47,000 going between Alexandria and Cairo. So this kind of gives you a reduced form of the matrix. You still have the same numbers in there, apart from the diagonals that might not be of use, but it really allows you to sort of view the data in the R console and actually work with the data itself. Okay, so in the final section on these slides, we'll talk about a few summary functions. So in the MIG-S package, there are a few functions that can help summarize migration data, and can accept. These functions can accept data inputs that can either be a matrix or arrays even, or data frames. So it doesn't matter what format the data is provided to these functions, they will give you the sort of same output. So the sum bilat function calculates the counter flows and the net flows. So what this does, it creates, takes the matrix or the data frame, and then outputs a data frame with the different origin destination combinations, and then the flow. So just like we had with as.dataframe.table, but then we have these additional helper columns, one telling us about the corridor. So we can sort of see this is the flow from B to A. One about the pair. So this is a AB pair, and this is an AB pair, even though it's going from A to B. This one's going from B to A. And for each flow, we have the counter flow. So this is the value in the diagonal of the reflection of the diagonal, the migration matrix. And then we can get the net flow for a given pair, and also the interchange. So this is the sum of the flow and the counter flow. So we can see which corridor, which migration pairs have the sort of most back and forward migration. Okay, so we can apply that to multiple sort of arrays or even data frames that have multiple like detailed migration data. So that by that again, I mean it's like not just origin destination flows, but it might be origin destination sex in this case. And to do that, we need to use this group by argument of dplyr in tidyverse. So here I take the data frame D1, which was the data frame of the original sex array. I group by sex, and then I do the sum bilateral. And then this adds this sex column in here as well. So if I wanted to sum over the sexes, then I could just go straight to D1 sum bilateral. But if you want to keep the sexes separate and not sum over them, then you need to use this group by function in dplyr. Okay. So alongside the sum bilateral function, there's also a sum region function. And this provides a summary in migration, out migration, net migration, and turnover totals for each migration, each region in the matrix or data frame. So again, it will accept a matrix, or it will also accept a data frame object. And yeah, you can see with the original matrix that we created right at the start, we have got the summary out migration, in migration, turnover, and net migration summaries for each region of the matrix for the 4 regions. But there's also a sum country function, and it works exactly the same as sum region, but it just provides labels for the columns that are relevant to international migration. So I think there's an example here. Yeah, so we get the same values out as we would do using sum region. Here I'm using a different data frame. That's why I'm getting different values from the previous slide. You can see the main point I'm trying to make is that when we use some country, we don't get out MIG, we get ME, and we don't get in MIG, we get in. in as the column totals. But the format is the same. So these some region and some country functions can also be applied to very large data sets, where again, we need to use the group by function to do that. So just to demonstrate, I'm using these estimated flows that we produced in 2019. Just downloaded this data straight into R from Figshare using the URL here. You can see this is a very big data frame with 235,000 rows and 9 columns. These are estimates of international migration between each origin and destination country and in 5-year periods. So this is the first year of the 1990 to 1995 period. And there are 6 different estimates based on different methods. So just an example with some country using sort of a big proper data frame. Here we take that data that we read into R, then we're just going to filter to the first period. And then we're going to sum some countries, sum over the countries to get the immigration turnover and net migration for all what we've got here, 197 countries. Okay, so one thing to note is in this argument, I'm setting what the name of the flow column is here. So here I'm using the column DAPP flows, which is one of these methods used to estimate the international migration. So in this some country and some bilat, these functions, they assume that the origin column in the data that you're passing to it is called ORIG, and it assumes the destination column is called DEST, DEST, and it assumes the flow column is called flow, FLOW. But if that is not the case, then you need to state what the flow column is. So in this case, I say it's equal to this DAPP close. Okay. There's a second example where I'm using the group by function in dplyr. I'm grouping by the years, and then I'm summing the country flows for this set of estimates, and then I'm going to arrange by the country. So again, you can see we get this time 1,200 for the 6 different periods and the 200 countries. So for each year, we've got estimated the emigration and the immigration, the turnover and migration from the different methods for the different. Okay, and then finally in the slide, the last function I'm going to discuss is this sum lump function. So this can be used to aggregate up flows in smaller regions. And so we do that by specifying a threshold in the threshold argument. It tells you all the flows less than this value should be put into like an other category or a rest of world sort of category or rest of country category. Yeah, and so this threshold can be either applied to the flow values, which is done by default, or to the in and out migration to totals. So there's an argument to show to say how to apply the threshold. So this sort of lumping of data can be useful when it comes to plotting the data. It might be that you have many small regions and you just want to create like an other category rather than visualizing all the small regions, because they might clutter the plot, for example. So to do that, an example here, we've got this original migration matrix, and here I'm going to set a threshold to 50. And you see what comes out is a table. We've got 5 columns. Hopefully this last one, you can see it's saying other. So the largest flows, the ones greater than or equal to 50 remain, but all the other flows are put into these other to other flow sort of migration corridors. Okay, so a more practical example again is using this sort of estimated international migration flow data, where I'm going to filter just the last period, this 2015 period, and then I'm going to add on using the country codes packages. I'm going to add on the regions of each country. So I'm saying all these all African countries in the origins. So I'm using the origin column, and I'm saying it's a 3-letter country code. I want to output a region that the 3-letter country code belongs to, and the same for the destinations, doing the same. And then you see we've got the 2 additional columns in our data set. So then we can use a sum lump with a bigger threshold than before. Here we set it to 100,000, and this just then allows us to really show the biggest sort of flows going on. Because I group by the origin and destination regions, it's within each region to region sort of streams, we can see the biggest flows and the smallest flows are some categorized, aggregated into these other rows. Okay, so yeah, there's an exercise to, if you want some practice, to go through these through and get familiar with some of these functions that I talked about. Mainly it's like creating matrices and arrays and playing with some region and some country. Okay, and then yeah, these are just references to what I used in the slides there before. Okay, let me switch on to the second set of slides proper, which is on estimating bilateral migration. So a common problem with bilateral migration data is that it's often unavailable or outdated. So it might be that we have to rely on detailed migration data, origin destination migration data that was taken from the last census, where the last census could be like 7 or 8 years ago, for example. And it might be that we do have some knowledge about current migration patterns, but not at the detail of an origin destination flow, or perhaps even more detail, like age-specific origin destination flows. We might be in a situation that I've sort of mapped out here, where we have some auxiliary data, perhaps from a census in the past, of the origin destination flows, and then at the current point of time, we just know that how many people have arrived into each region and how many people are left into each region. So in this situation, the marginal totals are sort of known for the current period, but the cell values are not known. This is a typo, right? Known. So these can be estimated using a range of different methods. So yeah, similar data estimation challenges exist for more detailed bilateral migration flow tables. For example, you might know the in and out migration totals by age in each region, but the origin destination migration flow tables for each age group is missing. So, this kind of data is required for any kind of multi-regional cohort component models. You need origin destination by age flow tables, and yeah, it might. And so in that case, you would again need to use the methods that we are going to use to help generate those detailed estimated flows. Another example is in when you come to estimate international migration flows. There's been a number of methods proposed that sort of set up data situations like this, where you have the sort of known marginal totals, and you want to estimate the unknown origin destination totals, and that's done by using stock data. I'm going to too deeply here. So one approach to sort of estimate these values in a contingency table based on known marginal tables and an initial contingency table is the iterative proportional fitting procedure. So this was first described by Deming and Stephen, and then later there's been other papers also close to the time sort of describing it. And it's been widely studied in a number of different disciplines and has a number of different synonyms. So, for example, statisticians tend to call it raking, mathematicians might call it matrix scaling, economists might call it the RAS algorithm, geographers might call it like a biproportional fitting. There's lots of different names. So there's a couple of nice papers that give a good overview of their applications of IPFP. This one by Lovelace talks more generally about social sciences. And Nick Lomax and Paul Norman have a very nice paper looking more specific to demography, not just migration, but also other areas where these IPFP methods have been used, and also kind of give a good starter guide. So mathematically, what happens in the IPFP algorithm is that you start with a seed matrix. We saw on the left-hand side, this auxiliary table, this MIJ, and we say that's sort of set to our current iteration. So this is the iteration number 0. So it's our first guess, our initial guess of the estimated origin destination flows, this mu ij. And in the second step, we say this mu ij and the next estimated next estimated set of flows is going to be equivalent to the original set of migration flows, scaled by the NI plus. So these is the target row totals, and then divided by the current row totals. And then we take that value that's been sort of rescaled seed values and use that up here in the next step, where we take those values and divide by the column totals of the first iteration, and then multiply by the column totals in the target. And then this sort of procedure back and forth carries on iteratively until you get to a converged estimate. So I thought I would show that more in tables rather than going more deeply into the equations. This is just the same similar data that we had before with the origin destination flow tables. And we can see the in-migration totals on the first column here. So these are the totals down here. I put them into one column and also put them alongside the out-migration totals. And it provides the third column here, the basis for the third column, which is the net migration totals. Okay, and then what we want to do is say that this is old data in a census, and we have a target in and out migration, just like we set up at the beginning of these slides. So what we do, we take the old data and use it as a seed. And then what we're going to do is first go row-wise, where we're going to take the out migration total here, 200, and divide it by, and say we need to scale it up to 250. So we need to scale everything on this row by a factor of 250 divided by 200, so 1.25. This 100 is going to be multiplied by 1.25, 30 by 1.25, and 70 by 1.25. Then we're going to do a similar thing for the second row, but they're going to be scaled up by a factor of 75 over 100, and the third row 125 over 135, and so on. So when we do that first sort of sweep through, we can see these values are all multiplied by 1.25, and that means that the current iteration, the estimated values, are matching the target values that we want to hit. Okay, but when we look at the immigration totals, the in-migration totals on the column totals here, they are not matching the target. So this is what the second step of the IPFP does, is look column-wise and divides. So for example, in column A, region A, we're going to multiply this 37.5 by a factor of what is it? The target here of A is 150 divided by 139.21. Then we're going to divide those in column B by 200 divided by 215.1. So we get these scaling factors applied column-wise in the next step. So you can see we do that, and then we get our current iteration as matching the targets, but the row values now are no longer matching. So then we go back and sweep along across the rows. So now they match, but the columns don't match, and then we keep on going through the columns, then the rows, and the columns, then the rows, then the columns, and the rows. Now, what happens is, as you keep on doing this, some of the values, some of the rows, some of the regions, they start to converge. And you see the differences are getting smaller and smaller each time. For example, at this stage, everything has converged. We've just done a column sweep, and the rows totals are matching everywhere apart from in row A, in region A. So we just keep on doing this a little bit more, and then it's all fully converged, where you keep on going row, column, until you meet some sort of minimum threshold that you're sort of happy that the differences are so small that you're going to stop the algorithm. Okay, so this is really the basis of the IPFP. So there's been some discussion on like what do we use as this auxiliary table that, especially when we come to migration estimation. So Franz Willekens wrote in 1999 that sort of a typical approach is, or the best approach might be to use past data on migration flows. Sometimes they don't exist, and in such cases you might want to consider using perhaps a stock table or a different measure of migration, or you might consider using some distance matrix or travel costs between the pairs of origin destinations where no migration data exists. But there really hasn't been too much testing on what what auxiliary data would provide the best estimates. It's very much an under-researched area of the IPFP and its application in migration estimation. Okay, so how do we do this in R? So the best way to do it in R by far, I think, is this MIPFP package, which has a nice paper accompanying the package. It implements the IPFP via this IPFP function with a big I. And this can be used for multiple dimensions, not just the classic case for the origin and destination. Yeah, it requires 3 inputs, so 3 arguments. There's a seed argument, a target list argument, and a target data argument. So the seed argument is just like we see before, this auxiliary data, this past data that can aid in the estimation. That's sort of the starting point for the estimation. And then the target list and target data sort of work in unison. So the target list is a R list of the dimensions that are being targeted. And the target data is the list of the targets related to the target list. Okay, we talk a bit more detail about the target list. So the target list is going to be some set of values that you're saying you want to match. So for example, if you just want to match the rows, then you would write target list is equal to list 1. Or for example, here, but if you've got a single target that's a column totals target, then you write target list is equal to 2. So, you know, R always sees the rows as the first dimension, the columns as the second dimension, and then tables and tables of tables as the third and fourth dimension, and so on. Okay, so if you want multiple targets, like we just had in the previous example, then you can write this as a list 1, 2, for example, if we want to have row and column targets. And yeah, if you want to sum over specific cells, so perhaps you have a 3-dimension table and you just want to target a specific origin destination combination, then you can write a target list with the concatenate function, the C here, where we join together the saying that we have a single target specific to an origin destination pair. Okay, so here's an example of it in operation. Again, just building this basic matrix that we had in the last slide. You can use the add margins function. So we can see the sort of auxiliary data, the past data set up here with their margin totals. And then we can provide an origin and destination totals. And here I'm just naming them just to keep track of everything. I use the dimension names. So we can see these are the new targets that we're going to try and match the data to. And we can just check that these origin totals and destination totals, they need to match, right? Otherwise, we will get some warning messages from IPFP if they don't match. Okay, and then the implementation of IPFP, we set the seed as this M0 matrix. We say we want to target the rows and the columns. So we write list 1, 2. And then we say the target data. So the row columns are going to be in this list as the first component, and the second component are column totals by again, you know, these target list and target data are working in unison. So what outputs is what prints out the call and the method is saying that we've got convergence, the IPFP, and then we get the estimates here. Okay. We can save those results and inspect them a little bit. And so for example, here I'm saving them as a Y0. And then if I look at the X hat component of the Y0s, that's where the actual estimates themselves are stored, and do add margins, and we can see the row totals and the column totals from our targets are present in the estimated values, in the converged estimated values. So a second, a bit more complicated example is something that we might look at. So for example, we might have auxiliary data from the census, like detailed migration flows by sexes. But in the current period, we might just know the in and out flows into and out of each region. So this is to sort of operate this in the IPFP function and a more complex data situation. We can create this data and sort of show how it works. So here I'm just creating the array that was shown here. Bringing in the data there, and then I'm going to use the xtabs function to convert it to an array, the data frame. So IPFP, the function requires data in this array format, and then here I'm just showing the add margins, so we can sort of see the current or of the past data, the row and column totals. And this is over both of the summing over secs. These are the origin and destination flow totals. And then we can use our old row totals and column totals rather than just creating new ones. I'm just taking the target in and out flows. So you can see these are not matching the origin totals, don't match in the past data, don't match our current totals that we want to target. So we can move this, provide this data to the IPFP functions, where we're saying we want to target the row and column totals that are in the target data, just like we had before. And in this case, the seed is changed from a two-way migration matrix to a three-way migration array by origin, destination, and sex. So what comes out is the array itself, the sex and the female and the male arrays of the estimated flows, where the origin sums are going to match the totals. So you see the detailed origin sums, the sex-specific origin sums don't match the totals. But when we sum over the A, for example, there's 192.6 plus this 57.4, that's going to match the target of 250 that was provided in its origin total. So here I'm taking, again, the estimated flows, just summing over the sexes. So we can see that we have matched our targets that we used in the algorithm. So hopefully you can see this IPFP function has a lot of power to it, that it can take many different dimensions or data structures, let's say, and allows you to adapt to different data situations to provide estimates of detailed bilateral migration data flows. Okay, this last slide is just using as.dataframe.table to put it into a data frame in case you want to export the data to Excel. Okay, and then to finish up these slides, I'll talk about some older methods and some newer methods on constraining origin destination flows to net migration totals. So they're a little bit like IPFP, except in the classic data situation where we had the row and the column totals. In this case, we don't have the row and column totals. We just have the net migration total. So it's even less information that we need to constrain to. So Plain in 1981 developed this sort of proportional adjustment algorithm for estimating bilateral migration flows to match both a constraint on the net migration of the in and out migration totals, and also the total sum of the all bilateral migration flow data. So his method required data on the past, some kind of seed, the past bilateral migration flows, and then a target of the total of the total migration flows over the whole system, and also a target net migration flows. And also in his algorithm, he required a distance matrix to correspond to the origin destination flows. So at the moment, there's no way to do this in R, but there is a method called a CM net total, constrained maximization for a net migration total and a grand total. Yeah. So this sort of works very similar, gives very similar results to the Plain paper, but it doesn't use a distance matrix as well in the algorithm. So it doesn't give exactly the same results as he got in his paper. But here's an example of it in practice. Here we've got the original data frame that we've shown before. That might be the auxiliary data frame from the census. And we can see the net migration from this data is minus 70, 60, and minus 40. And that past data frame. It might be that we have some target net migration that we want to meet. Perhaps we work that out via demographic accounting. So we know from the differences in the populations and the births and deaths in a more recent time period that the net migration is minus 100, 125, minus 75, and 50. And so what we want to do is try to estimate detailed bilateral migration flows. They're going to match these net migration totals. And in the sort of Plain method and this method in CM net total, we also set a constraint for the total grand total of how many migrants there are going to be in the whole system. So we have to provide this total as well. Here we're providing the seed as in the M argument, just put this verbose, just make sure it doesn't print out lots of the convergence tracing of the convergence. So we're saving this algorithm, the results of this algorithm, in this Y1. And then when we print out this object, we can see that this is the modified origin destination flow matrix that has net migration totals that match the constraint. So we can check that using some region where we get this net migration column. So there's some regions done on the estimates themselves. So this gives the net migration estimates that match what are in the constraint. So remember, in the original data, M0, the net migration was minus 70, 60, minus 1450. And the new one, it's minus 100, 125, minus 75, and 50. Just use that seed data and update it to match this net migration data. And also, it's the grand total is also 600. Okay, I didn't run. Yeah, it's 600. If we rounded this data, it will get to 600. So it's matching these two constraints. Okay, so I think with this method, it's sort of an area that I'm working on a little bit on the side. So this method of planes, it's not been widely adopted. I think the paper has maybe 30 or 40 citations over like the 40 years. I think that's because in many countries, this restriction, this requirement that you have also provide a grand total of the number of migrants is typically not known. So you might be, you can imagine if you knew the overall number of migrants in the system, you would probably be getting that from some comprehensive population register where you might already know the bilateral migration flows. And so you don't need to use an algorithm to estimate them. Or it might be that you already know the total in and out migration flows. In that case, you wouldn't need a net constrained algorithm to do that. Use IPFP. So in recent years, I have been working on a method with Peter Smith at University of Southampton that constrains only to the net migration totals. So similar to before, but you just have a constraint on the net migration totals. So yeah, like I said, this is unpublished and use it at your own risk, but it's available in this CM net function in the MIGS package. But I think this might be more useful than the plain method, because I could imagine that there are situations, or we found situations where you might have this past migration flow data or current migration flow data from surveys or administrative data, and you also know what the net migration totals are, but they're not the net migration sort of estimates obtained from like demographic accounting don't match what you get in the survey data and bilateral migration flows from the survey data. So you might want to adjust the survey data with the bilateral migration flows to match the sort of the net migration totals that you have got through demographic accounting and believe are reliable. So this is just an example of its implementation. In R, we use the CM net function. We say these are our net totals. We don't have to provide any grand total, and then we give the offset, the seed, sorry, as the M0 matrix again. Again, we get then the estimates out. We say them as Y2. We get the net migration totals are met in the estimates. The target totals are met in the estimates, but there's no. See, these values don't go to 600, which was the target total from the previous algorithm. They just go to independent sort of target value. Okay, so in exercise 7, there's some sort of exercises to practice playing with mainly the IPFP function in the MIPFP package, and yeah, that's using data from the UK, from the sort of census data as the seeds, and NHS data from the health service, and from the student data combined for the current sort of in and out totals. So it's more practical application than I've sort of shown in the slides, where you're actually using real data to do that. And here are just some references to the papers that I mentioned in these slides. Okay, so then we can go to the last set of slides, which is on chord diagrams for visualizing bilateral migration flows or stock or any migration data. So visualizing bilateral migration data is not straightforward. It's often difficult to represent both the geographic and the temporal aspect of migration at the same time on a single plot. So there's been many different approaches used over the decades to visualize migration flows, and I think, or however you do it, you're probably bound to fail. You can't please everybody. Not everybody's going to be happy with whatever visualization that you come up with. But two non-map based approaches are chord diagrams and alluvial or Sankey plots that we talk about in the handbook. And I tend to prefer these non-map based approaches because they give a bit of a sort of clearer visual guide to what is going on with the migration flows, especially for small geographic areas, where if you put them on a map, they might be overwhelmed. So for example, if you're looking at European migration, Luxembourg or Belgium or these Benelux countries, big players in the system, but it's often difficult to disentangle what's going on when you start playing around with a map on a single static plot and looking at those smaller countries. And these non-map based approaches also allow you to include more detailed data or include more bilateral connections than you might do when you're using a map. There's also like a very nice paper in Mobilities that came out last year on migration map trap and talking about the use of invasion arrows to visualize migration. So they sort of argue that the cartographies of these migration maps tends to peddle sort of crude distortions of migration, and it has this sort of based on a xenophobic tradition, propaganda cartography, and they sort of call for more scientifically robust, critical and created geographies. So by migration map, they mean, and I mean maps where you have these arrows essentially on maps that might be drawn from sort of military history. So this is a screenshot from the Dad's Army. It's a British sitcom in I think the 50s and 60s that sort of was illustrated these movements of Germans and the defending forces of the Dad's Army in the UK. And they sort of reference these maps a lot, these sort of military maps, and how even today, so this is a map from Frontex, the European Borders Agency, they are using these kind of invasion connotations in their migration maps. So here, this is showing the movements during 2014 and 2015 of border crossings into the European Union. But they make the point that these arrows, firstly, they're red, which has its own connotation, but also that the size of these arrows, I mean, they've got to fit it on the map, okay, but it really looks like Europe's just going to be overwhelmed by hundreds of millions of migrants. In fact, the numbers are in the hundreds of thousands, much smaller. And they're also sort of, this sort of non-specified people coming from a certain area. Like it doesn't quite work on a map, right? That you have these non-specified flows, a big part of that, and they've just put them in the middle of the Indian Ocean here. Okay, so what we're going to concentrate on the rest of the talk here is looking at chord diagrams as one way to visualize migration without a map. And these first chord diagrams were first introduced in 2007 in this New York Times article. Let me switch. So this is the printout from the New York Times article. And they're essentially designed for geneticists with genetics in mind, looking at the linkages between these different species. And there's not just these chords in the middle that we're going to focus on, but they also have like these bar charts on the sectors here, and lots of different information about what is going on here. And you can see some other types of comparisons using the chord diagrams here. Okay, so these have been very useful in genetics to identify and analyze the similarities and differences in genomes, and they're playing the relationships between pairs of positions using these ribbons or chords that encode the position, size, and orientation of the elements. And this plot that was first used in New York Times was then or the software behind it was developed as, or has been continued to be developed into this Circus software, which was written in Perl, in the Perl language. So if you go to the website here, then there are many examples of the use of Circus plots, most of which is outside of migration data. So the first interactive chord diagrams were introduced in, this is a typo, it should be D3, D3 language by Mike Bostock. And they were first used for migration data by Chris Walker, who showed a plot like this, showing the migration between different US states. Or you can see, for example, the chord going here from New York to Florida. In fact, this was like, if you go to the website, it's interactive. So if you mouse over on the website, you could see, it would say like how many thousands or hundreds of people are moving between New York and Florida, and how many are on the return. Yeah, so yeah, it doesn't really show the direction of the move until you mouse over. So it's a bit difficult to tell whether this is really a New York to Florida flow or Florida to New York flow. So Nicholas Sander adapted this sort of visualizations to add some kind of directionality to the plot for the flows that was first used in this paper that we did in Science. And there's still an interactive version of this plot if you follow this link on the big website. So this is just from the Science paper, the plot showing the directionality, where she added some arrows to the plot here. And the main thing was that she deleted, I don't know how you say this, removed part of the chord to show where the arrivals are coming up here. So these where it's connected, the sector to the region. This is the leaving part of the movement, and then they're arriving here. So you can see these all moves out of sub-Saharan Africa, and these are moves into out of North America, and these are moves into North America. Okay, so I still believe that using these kind of plots, there's still some drawbacks to these Circus plots. So the first is when you use the Circus software, the inflows are plotted first on each sector. So as I see here, you've got all the inflows coming in here, and then the outflows out of North America. And that's kind of counterintuitive. I think when you read the plot and you look across the sector, you probably think about outflows before you think about inflows. Like people move out before they move in, right? It follows the sort of a temporal direction. Also, you get these chords for the smaller flows tend to be plotted. Well, the plotting order is a bit random, so you can see you might get these smaller flows being plotted on top of all the larger flows. In other cases, you might hide the smaller flows. Yeah, I think it's still difficult to detect the direction of the flows. You sort of need to think a little bit about what are the directions. Usually there's a guide provided that can help you, but it's not straight away informative on how it's working. And the last point is that to get these arrows and to do the touches of add in these blank spaces, that usually requires, when you're doing the static plots, at least some kind of additional software. So whether that be Photoshop or Illustrator. So that gets very problematic when you want to update the plot or replicate the plot for different situations. It's a switch between the two. Of course, it's something that R gets around, that we sort of you can sort of program everything in R in a single bit of software. So these plots, at least these Circus styles plots, are available in a number of R packages. Perhaps the nicest one is this Circleize R package by you, which is probably more accessible, which doesn't have a lot of genomic terms in the function codes, so a bit easier to understand how the code works. And it's built entirely on the base R graphics, so it doesn't use a ggplot or any other graphic system. It uses base R, and importantly, it includes a chord diagram function that has extensive documentation. So if you go to the Circleize book website, there's a link in the slides here. You can see there's three chapters there on how to use the chord diagram function. So to illustrate it, I'm going to use the UN stock data, which I just tidied in this data frame here. So we have thousands of rows here, but we're just going to select filter to the codes for the continents. So we just have the continent to continent flows here. And we also filter to the 2020, the latest data. And we make sure we only have the origin, destination, and stock column. So that's an important thing that for the chord diagram function in Circleize, it can take either a matrix or a data frame. But when you use a data frame, it requires the data in this format. You have the origin first column, the destination second column, and then the numeric value of the connections. So it could be stock or flow. It doesn't, in each of these columns, the column names are kind of irrelevant, but it's looking for the value of the connections in the third column here. And if you have more columns, then it will throw an error, or it might get confused and you might get a messy plot. So it's always good to make sure you only have the 3 columns when you're using this chord diagram. Okay, so like I said, you can provide the data as a matrix or a data frame, and I tend to prefer working with the data frames just because usually you're reading data frames into R, and it's easier to use dplyr and the IUSSP packages to manipulate the data frames rather than when you're working with matrix. This is the point I was saying before, that the first 3 columns should correspond to the origin, destination, and the size of the connection. And then the columns can take any name, but they must be in that order. And it will work with tables. They don't have to be data.frames, as I mentioned above. So there are many options in chord diagram that are by default not ideal for displaying migration data. Again, this package will be written mostly with geneticists in mind. So here's the sort of default plot when we pass the data to it. So one thing you'll notice is that there's in this case, it assigns the colors randomly. And in this case, it's assigned a white color for Asia, and this purple color for Latin America, and so on. But and you can see like the numbers are a bit small and the labels are not great. They look a little bit funny. They can be tidied up. So I think the first thing to do always is to focus on the scale of the data. So it's often like we don't want these. It's easier to read non-scientific notation for the scale of the migration data. So in this case, I'm going to divide all the stock column by 1,000,000, and this allows us to get easier to read scales on there. Okay, and again, you see we generated a second plot and the colors change. That's a feature of the chord diagram function. We can set the colors, but if we don't set them, then they're going to change every time we do a plot. It's just randomly generated. So as I said, there's over 40 arguments in chord diagram, and many of the default settings are not ideal for migration data. Also, if you want to change the labels or change the format of the axes, the appearances of the axes, it gets very complicated very quickly. So they're actually done outside of the chord diagram function. There's no way to control these labels and the axes, or not a lot of control in this chord diagram function. So in recent months, I've written this mig-chord function in MigS that piggybacks on the chord diagram function. So it's kind of within this mig-chord function. But what I've done is set the parameters on many of the parameters in the chord diagram function to sensible defaults specific for migration data. And it also sets a fixed default color palette. And we'll talk a bit more at the end about how we can change the colors. And it also has some additional arguments to help with label placement and the axis appearance. So to demonstrate that, I just load the MigS package and then do mig-chord on the data frame. And then you can see we get the plot here. So I've changed a lot from the default, set the colors to a sort of standard kind of rainbow umbrella color palette. And then I've added the directionality using these big arrowheads, which is a setting within chord diagram we can set. I've also added this white space here, so the arrows aren't coming exactly to the sector edge. Yeah, but I think overall it looks a little bit better than the default from the chord diagram. It's easier to tell the direction at least. Okay, so the labels kind of always a little bit fiddly, but I think in the mig-chord function, it's a little bit easier. But I think when you get to worry about the labels, it's good to use sort of a helper data set to help manage the labels. So here I just create a data frame just with one column at the moment, with just the union of the origin and destination names. So I have them in the column here. And then I'm going to use the string R package to create nicer labels that are not in capital, not capitalized. And here I split the labels into two. I'm using string to title to put the user title case. And then I'm removing the and the in Latin America and the Caribbean just to and the Caribbean. And then I'm using string wrap to add in these new lines, which is signified by the /n. It's a line break in R. So these are added when the string length is greater than 14 in appropriate places. And then I use that line break to create two additional label columns, one for a short label for the first half of the label, and the second for the second half of the label that hopefully you will see us use in the next few slides. Okay, so to pass these labels to the make chord function, we need to create a named vector. And that is a vector where we have the names in green here, the kind of new names that we want to pass, and in the black the corresponding sort of names in the data set. So it allows you to, it sort of looks in the data set and then looks for like Africa in capital letters and then replaces it in the plot with Africa in lowercase letters. So we create the region lab named vector by taking the data frame R that we had before, and we're going to select the region and the lab column, and then we're going to deframe, which converts it from a data frame into a named vector that is printed out here. And then we pass that named vector to the make chord function using the lab argument. Okay, and we can see that it's passed these lowercase labels with the line breaks in them that was stored way back here in this lab, originally created in this lab column here. Okay, so we can also pass the named vectors to lab bend arguments. So if we just want the labels to be bending rather than sort of these horizontal style, then we can use this lab bend one argument. And if we want to put them on two lines, then we can use these labels that are split up in the lab 1 and lab 2 columns. See, so here we've got Africa, so there's no lab 2 column, but here we've got Latin America, and Caribbean is on the second label. So again, we're passing these named vectors into the make chord function. For the first plot, where we've just got one bending label, we can see the values here. The label values here, and the plot becomes a little bit bigger because you've got a bit more space to play with. That's done automatically through the make chord function. And this is the second plot where we put them on, where we've used the two labels over two lines. Okay, so we can control the label space, the positions for the labels, the amount of space to put the labels in, using a number of different methods. So one is to use this pre-allocated tracks argument, then passed directly to the chord diagram, and that controls the share of the plot that's there for plotting the labels of the track. There's also a label size, which is a kind of make chord argument that adjusts the font size of the labels, and a label nudge argument that can shift the labels towards or away the axes by either providing a negative or a positive number. So here I just set the allocated tracks to 0.1. So this track height can go between 0 and 1. And I think by default it's well, it changes depending on how the labels are. This is saying 10% of the space in the plot should be reserved, like the outer 10% should be reserved for the labels. So you could increase that to 20% or 30% by changing that to 0.2, 0.3. So it really depends on how big your labels are and how many line breaks you've got. So it's always fiddly because it's going to change for different region geographies. And here I'm changing the label size to 0.8. I think by default it's 1. The label nudge minus 0.3. So I'm kind of nudging the labels towards the sector axis. So you can see this is the plot. So we've got 10% space. So it's a little bit bigger than before. I think the overall plot is a bit bigger and we've got less space for the labels. You can see that a little bit, maybe a bit too close with this label nudge coming into the size here. And yeah, the label size is a bit smaller than before, the font size here. Yeah, you can see that a little bit bigger. Okay, so there are also options to control in the MIG chord function the axis breaks. So how many how much labels there are on the axes and the size of the font on the axes. So in this case, I'm just creating a new region label named vector. This time without the line breaks in them, just so it's a little bit neater. I'm changing the label size. This time I'm making it to 1.2. I'm going to put axis breaks at every 10 million rather than every 20 million was the default, I think. Yeah, here you can see they're going every 20 million. We're going to put them at every 10 million. I want to change the size of the axis font to 1. So I think by default, that's, yeah, 0.8. So here we get the bigger axis labels. We get the axis labels at every 10 million. And yeah, we also get these new labels that are without the line breaks in them. So again, these minor tweaks you can do quite easily now with the MIG chord function that were quite difficult to play around with using the chord diagram. Okay, so finally, well, penultimately, we talk about the sector ordering. So the sector ordering, the order that the regions appear in the plot are done by default alphabetically. But we can specify that, control that using this order argument, where we have to pass a vector of names to the MIG chord function, or even it goes straight to the chord diagram function. So to do that, yeah, to order the sectors is definitely an art, not a science. So I think I've tried, whenever I've done these plots, I try to keep neighboring regions close to each other. So you don't have two regions that are, yeah, that are sort of at the other side of the world or the other side of the country, that they tend to be on the other sides of the chord diagram. So in this case, I create a vector where I just say the North America should be, I forgot, but yeah, I'm saying I create this region order vector here, which, okay, let's go back. The region order is going to be 2, 4, 3, 6, 1, 5. Let's take in the original data, where Africa is going to be 2, Asia is going to be 3, Europe's going to be 4, Latin America is going to be 5, I think. Yeah, so we can 2, 4, 3, 6. So Latin America is 6. Okay, so I applied that column to the original data frame, and I arranged it in this order, so so that we can pass this column to the MIG chord. So you can see order is equal to R$ region. So it's directly taking this this column, say this is going to be the order we want the region plotted to. So now we can see North America appears first at the top here, then Africa, then Europe, then Asia, and following the order in the help data frame that we've set up here. Okay, so if we want to control other things about the plot, so for example, the orientation or the gaps, we can do that in chord diagram using the circus par function. But the MIG chord function feeds also directly into the circus par function as well. So you can use the same argument names in circus par as you do in MIG chord. So if we want to change like the spacings between the sectors, we can use the gap.degree argument. So by default, that's 1. So here we're going to change it to 10 in the next plot. And we can also change the start degree, for example. So by default, yeah, 0 corresponds to 3 o'clock. So we can change that, for example, here to 0 to make sure to sort of twist the plot around so that it starts at 3 o'clock. I'm not sure why it starts at 3 o'clock, but that is a chord diagram function in the circularized package. Okay, so here's the example with the bigger gap where we set gap.degree is equal to 10. You can see these gaps in here, much larger than before when we had a 1 degree gap. And this is with the start degree is 90. So North America was up here at 12 o'clock before, and now it's at 3 o'clock with this start degree of 90. So yeah, okay. Okay, so this MIG chord function uses this set color palette, but we can generate our own color palette and use that. And we can sort of affect the colors in a couple of ways. One is using grid dot color, which corresponds to the sectors, the regions, the countries, or the areas. And the second is the transparency, which by default is set to 0.25. So in this bit of code, I'm just, with the helper data set, I'm just adding this column and we're going to pass these named colors into the MIG-Chord function. And so this provides this plot here where we've got the colors as they are, according to the names that we gave them. In the second example with colors, I'm using the R color brewer package to brew a color set based on the set one color brewer palette. So if you go to this website, there's lots of named palettes, like default palettes, and you can use the name. So here I'm using a set one, and you say I want 6 colors because I've got 6 regions. So this fills in this color 2, color 2 column. And the third color 3 column, I've just created again another set of colors where I've got red for North America and gray for the other ones. So this kind of coloring can be useful when you want to highlight outflows from a particular region. So here I've run 3 different examples. The first one is using this R color brewer package, and the second one is again using the same set of colors, but setting the transparency to 0.5 rather than 0.25 the default. And the third one is using this set of red and gray colors. So here's an example of this color palette from our color brewer from the set one palette. And the second one, same color palette, but I've set the transparency to 0.25 rather than 0.5. You can see it's just affecting the transparency of the chords, not the sectors themselves. And the third one where we set the colors to gray, except in North America, where we set them to red. This might be useful if you want to particularly focus or highlight migration in and out of a particular section. We can do even more complicated things with colors. So there's a col argument that corresponds to the links themselves. So if you want to highlight particular links, we can do that by adding to the original data set that we're plotting. We can provide a column called a link color, or we can name it whatever we want. But in this case, I called it link color 1, where if the it's saying if the origin is Asia or the destination is Europe, then it's going to be a black color. If not, it's going to be a gray color. So for only this flow between Asia to Europe, we're going to have a black color. All the other ones are going to be gray. And there's also a link.visible argument in CircleEyes that we can pass through via MIG-Chord, where we can hide certain links. So it sort of sets the colors to transparent for selected links. So here I create a function, a column called show link. And here I said the origin or destination is Asia, then we want to show the links. But if it's false, then it's going to hide the links essentially. So we can pass these columns to the MIG-Chord function, and they go on to pass it to the chord diagram function. So we set the grid color as before, but here we're going to set the color of the links to $link, the link color 1, this column here. And the second plot, we're going to set link.visible based on the show link column in the migration data set. So this is the first example where we just set the link colors all to gray, except the link between Asia and Europe. So it's the same plot, just change the colors. And the second one, we have the same plot again, but we changed all the links that are not to or from Asia are being set to transparent, completely transparent. So they're kind of not plotted on that. So we still get these different colors for the folks coming in or stocks coming into Asia, but anything else going in or out of the other regions are not shown. Okay, so just a final word on saving. So I think it's always useful to save these plots, chord diagram plots, as PDFs, because they give you a scalable image. That means we can zoom in very closely and we can still see the chords in a lot of detail. Because if we use a PNG or any other graphic, these details will disappear, and they'll also cost us a lot of memory. But to save the chord as a PDF, we have to surround the code that we use. So here I just do a plot just with the labels. We have to surround it. First, we open the PDF using the PDF function. Say the file we want to save as, where we have to end with this .pdf, the file name that we want to create. Then we run the R code that plots into that file, and then we turn the plotting device off using def.off. So in the next two examples here, I just gave an example of creating an image file using PNG. And I said different resolutions. So when we create this PDF, this PDF is created by default with height and width of 7 inches. This is the default size of a PDF. And everything, all the code I wrote for mid-chord for the placement of the labels and everything, that all works assuming that you are plotting into a 7x7 size PDF. If you plot in a different size, it might come out slightly funny looking with some overlapping labels and chord diagram. Okay, so back to what I was saying. Yeah, when you plot these PNGs, I'm also plotting them into this height and width 7, but with different resolutions. But that's to illustrate the point that on this left-hand plot, we had the PNG with 100 pixels per inch. That was the resolution, and you can even see from here some of these chords are breaking up quite a bit. They're sort of losing the detail. With the PNG in the middle, it has a resolution of 500 pixels, so it looks okay, but you can see as you start to zoom in, if you had a bigger plot, you start to see these missing parts of the smaller chords. So you sort of reduce the quality here. And on the third one is the PDF, where we can see it sort of never goes away. We can zoom in as much as we like, will be fine, because it's a scale vector, scaled vector image. So yeah, we can increase the resolution of the PNGs even further, but come at the cost of larger file sizes. So here, this 500 pixels is already 4 times the size of the PDF once we saved it. Okay, and to finish, there's this exercise. Let's practice plotting from this paper, this Korean internal migration flows, using very similar sort of playing around with the different functionalities of the mid-chord function and the circularized chord diagram functions. And then these are the references to what I mentioned in the slide. Okay, so I think I leave it there. Feel free to contact me afterwards if you're watching this, if you're not watching this live, or I guess I can stick around in the question and answer session if there's any more questions. Okay, so I think I stopped the presentation there. Let's find the result. Okay.
Thank you, Guy. This is excellent. And thank you all for your loyalty to work through this curriculum. So Guy, if we have questions, please, I'll turn it to you, or it is yours, of course, this space.
Yeah, I mean, I guess it's difficult to take questions. Like usually when I've been doing this teaching before, sort of being in front of students and sort of sit down with the code and play around with it, check out any problems. But yeah, I guess, is there a maximum number of rows or columns for NEMA? So do you mean NEMA for the chord diagram or for the estimation stuff? Or I'm not quite sure what you are referring to there. Both. Let me see. So I think the chord diagram, yeah, and the IPF, they can take a lot of origins and destinations, so probably in the thousands. But obviously with the plot, like you don't want to put in so many origins and destinations because it just becomes like a big bowl of spaghetti. You might want to aggregate up origins and destinations into some higher level regions, like if you've got provinces, and move them up into some larger geographic areas. And then this is going to give a bit of a nicer plot, be easier for people to follow. But the IPF, I think it's going to work on many dimensions. Yeah, so you can have very detailed geographic areas. Yeah. Okay. Okay, so maybe that's the one question. Okay, she got it. Okay, yeah. So
let me ask one question, just very quick, and then I mean this is very intense, and you should all know that this has been recorded, and of course we'll have a Guy and James will have a manual coming out, so that's very exciting. And I think, Guy, I hope I can speak on your behalf, but I think we in the panel stand ready to continue to answer your questions and be responsive to your needs. but do you think in your own teaching and your own research, but I'm kind of interested about your own instruction of other students and colleagues, will you think about adopting some of these approaches over the next few months or years? What do you think? I could turn on Rasul, whom I know, to kind of think about that, because I know you're an active teacher scholar. So any thoughts about your engagement of this material in your own teaching and research?
I mean, for teaching, I think maybe it's more difficult to to like, you know, like I'm imagining one of our master's course that we it's probably too specialized, right? Too specialized. In. Maybe you could teach little parts of it in a part of a broader demographic methods course. I think this is where, you know, migration is always kind of ignored.
Yes.
And maybe it could come in as 1 or 2 weeks of
I will say our here at Colgate, we're an undergraduate institution, but our statisticians and our biologists have moved to largely using R for data analysis. So it's certainly it's increasing its kind of general framework. It seems to work with the minds of 18 to 20-year-olds, so 22-year-olds. So I think that's very exciting.
Yeah, I feel R is getting easier and easier to learn as a beginner. I mean, when I did it, it was such a struggle. I remember when I was doing my master's degree, like the computer would beep every time you made an error. I mean, it was just embarrassing. And now it's so much help out there, and there's so many packages to make things easier.
Okay, Matthias has a question.
Yes.
Yes, and we can unmute. Yeah. We can hear someone. Great.
Hello, many thanks. Very useful. Well, question R, I don't know, I just moved in another institutions and everybody's now using Python, and I just moved to R, and I feel I just made the wrong choice, but well, this will be for the next 10 years later. I will move to Python probably. Yeah, but I was just curious about what will be in these new R libraries that you will also include multi-region population projection models in these new libraries for the IUSSP?
I think what we're concentrating on is just like that outline I gave at the start. There's 9 parts, which is more on migration estimation rather than thinking about projections or decomposing by multi-regional assets. Because I have tried to look for people doing R packages or doing multi-regional analysis in R and the decompositions, but I can't find too much out there. But I think there's a case for it. There's loads of multi-state stuff, but especially like demographic multi-regional stuff. Yeah, I guess there's only really a few people that are doing that type of research. So, and you know, like James does a lot of it.
Yeah, exactly.
What about IUSSP? Is there a diversity of approaches in terms of the modeling programs there, or is there a kind of a coalescence around different approaches?
I feel like since I started at IUSSP, maybe there was only one, maybe not one or two, maybe a small share that were R users, but now it's, I think it's more in the majority, especially the younger researchers there have become more R users, and still get like the economists like on Stata and never going to use Stata. I think. Yeah, so it's still a mixture, but yeah.
So Matthias, that should give you some comfort.
Yeah, there's always Python. There's always these Python R debates, and yeah, I think like R has that sort of more statistical grounding. I think so. Maybe it's going to be a little bit more favorable.
No, it's just I just moved because it's so nice. You can do everything in one, as you said in the beginning, in one single environment. That's why I moved to.
And I think one real asset is that it kind of covers the whole. It concludes the circle in the process by moving into analysis and in communication. And if we don't close that circle, our results are not going to have the impact that they need to have. And I think R is very conducive to that. So
yeah, I would say as well, the one thing to mention about R is that there is package demo tools that is being developed with, I think mainly by Tim Reef. And yeah, but that package is amazing. It's really got so many things. It's not yet on CRAM, but I guess sooner or later it's being like developed, I think, with Melinda Gates' money and the UN. So it's really going to be a great addition for demographers, even now. But when it gets into CRAM, I think it's going to be very well help the R users.
Okay.
Great.
Well, unless there are other comments or questions, I think I very much heartfelt thank you to Guy and your work and your dedication to this project. You've really, over the past 4 years, really, you've delivered training sessions in Asia, several places in Asia, and in Egypt, in Cairo at the International Forum on Migration Statistics. So the ripples on the pond are really extending out. So thank you so much. And thank you all for attending and share this information if you can. So I will say good morning because it's still early morning here, and I will say goodbye to all our good colleagues. Thank you so much.
Okay. Yeah. Thanks, everyone.
Thank you very much, Guy. Thank